Okay, let's get started. Is there sound here? Okay, yes. Okay, so last time we start with the second harmonic generation, which is the most fundamental or most basic nonlinear effect, nonlinear optics effect, which basically is you shine a light, okay, a laser light to a piece of dielectric that has chi2 nonlinearity, and then at the output you will not only see the input light at frequency omega, you will also see a harmonic light at frequency 2 omega, and then the physics process. What really happened inside is that the media is able to convert two omega photon into one 2 omega photon. Okay, so it's a second harmonic generation. In this process, the energy and momentum, energy is conserved, which we actually proved with our coupled equation. Last time we get this. And also to get to here, we typically abandon all other frequency components except for omega and 2 omega. Okay, and the nonlinear polarization that's responsible for this second harmonic generation is the E squared term. Now, last time we stopped here with this. Nonlinear, with this coupled mode equation, which basically says is that your input light E1, will cause a change of E2 over Z, right? So your E2, if originally is 0, then it will start to grow. And what this equation says is that because of energy conservation, whenever E2 grow, your E1 has to decrease. Otherwise, it would, because your energy in E2 has to come from somewhere in E1, right? So this is the equation that fully describes the second harmonic generation, and of course it has analytical solution. But in this class, as in many cases, we prefer to simplify, to make assumptions, to simplify our mathematics, and to without losing much physics. Okay, so here we're going to do something that's very similar as well. We're going to work with second harmonic generation in something called non-depletion regime, where it has E1 much larger than E2. Okay, so what it typically says is that the gain, the number of photons that's being converted from omega to 2 omega is very small. That's why the E2 is much smaller than E1. In this case, you can throw away, on the right hand side any term that has E2 in it. That has E2 in it. So this will lead to IK partial E1 partial Z equal to 0, meaning E1 the amplitude of the amplitude of the input light does not change with the distance we propagate. Right. So the physics meaning of non-depletion regime is that the number of photons that's being converted to 2 omega is so small that you can neglect the impact. You can neglect the decrease of E1. Right. Suppose you have 10,000 photons and only one of them is converted to 2 omega, then you kind of don't have to worry about the change in E1. Okay, and one thing that you have to know, you have to be careful is that whenever you make this assumption, then when you make this assumption, then the energy conservation law is, the energy conservation is automatically violated, right? Because you gain photon for E2, but then you are not losing photon in E1, right? So you can no longer apply energy conservation, with here. But the benefit of this is very obvious. Is that now you reduce two coupled equation into one equation, and this equation is this, right? So you have partial E2 partial Z equal to I come to here, 2I mu naught epsilon naught omega square chi 2 and k2. Later k2 will be combined with these terms, and then you have E1. Now E1 is no longer a function of z because of the assumption here, non-depletion regime assumption here. E1z everywhere is equal to E1 naught, E1 0. So this is a number now. Okay, and then exponential I 2 k1 minus k2z. Okay, so now if you look at this equation, it's very, very simple, right? On the left-hand side is for the first order derivative, and then there's a bunch of constant here, and then the only thing that really is being related to z is this exponential, right? So what you can do is that you can use the boundary condition and do integration to get E2z, right? So you can do integration on both sides, and then on the left-hand side, what you will have is you have E2z equal to integration of this integration from 0 to, let me see here. Let's rewrite this. Okay. So if you do integration on both sides, on the left-hand side, what you will have is partial E2 partial z dz 0 to, for example, if the length is L, right? So from 0 to L, then what you get is, okay, this cancel each other. It's a very simple case. So E2, okay, z equal to L, z equal to 0 equal to L. So on the left-hand side, you have E2 L minus E2 0. Okay, and then on the right-hand side, this integration, you will have, okay, all this are just coefficient here. Okay, and then you have this integration of 0 L exponential I 2 k1 minus k2 z dz. And then we know that the integration of exponential alpha x dx is equal to alpha ke alpha x a and b. Okay, and the reason is if you do derivative of this, alpha will come out and cancel this, right? So the inverse of derivative is the integration. Okay, so if you keep going here, and then based on this, okay, the coefficient is I 2 k1 minus k2, and this come down, and I cancels I. You have 2 mu naught epsilon naught omega square chi 2 E1 square. Okay, k2, and then 2 k1 minus k2. And then you have, again, the exponential I 2 k1 minus k2, okay, L, right, because your integration from 0 to L, and minus when z equals 0. When z equals 0, the exponential is always 1, right? So you have this. Okay, and because the boundary condition, usually, okay, when you do second harmonic generation, there's no 2 omega input from the left-hand side, right? So in classical case, you can just cross this term. Okay, this is equal to 0. So in return, what you get is E2L at your output port equal to something like this. Okay, something like this. And if you're familiar with sinc function, okay, you know that okay, this is actually a sinc function. You have 2ki minus k2 here down here, and then you have 2k1 minus k2 up there in the exponential. So this is a periodic sinc function that periodic sinc function. Okay. So first of all, want to see a few observations of this result, right? So first of all, when you look at it, one, I would say a little bit shocking observation is that this expression, okay, is periodic. It's what it means is that okay, your E2, if this is L, okay, this is E2 squared. Look at this, is that this is periodic, right? So at the beginning, okay, L is 0. Well, if L is 0, right, at the very beginning Z is 0. If your nonlinear media is arbitrarily thin, then this is 1, cancel with 1, then you get nothing. Okay, but then what could really happen is that also when 2k1 minus k2 times L equals to 2 pi n, right? So periodically, this term will equal to 1, okay, and then we'll knock out all, well, and we will, it will make your E2 go back to 0, right? So if you really look at what's happening here, E2, if you take the amplitude square, what happens is that, okay, your periodic up and down, up and down, up and down, okay? Not the best drawing. So what it means is that this, the second harmonic generation, it's not that trivial that, okay, if you want more output, you just make your nonlinear media longer. It doesn't work that way, okay? It doesn't work that way. At some point, okay, when you hit the maximum, it will start to go down if you further increase the length of your nonlinear media. And later we'll know why. Okay, this is actually something called phase matching condition. Okay, and it ties to the very fact that the chi2 effect is phase sensitive. What I mean by that is that if you think about it, is that your E2, okay, if you really look at what this process is, look at this equation. Okay. What it says is that your E2, your differential of E2, okay, depends on E1 and then a phase factor here, okay, and a phase factor here. So because of this phase factor, at some places your differential is positive, so you're increasing, okay, you're adding your E2 up, but then at some other z, okay, when your length is long enough, okay, then you start to hit the point where this is this term and your E2 is off phase, okay, it's not synchronized anymore, and then you start to come down, okay, So this phase sensitive term is the reason why you will have this oscillation behavior. Okay, and and because of this, your E2 actually has a maximum, right? Your E2 has a maximum. Is that if you look at here, and how you get this term's maximum is fairly straightforward. You plot. Okay. This is real part, This is imaginary part of this equation, and of the what's in this bracket, right? And then you have -1 here is here, -1. And then what you want is the magnitude or amplitude of this is maximized, right? Because U2, okay, is a field, and then even if it means negative, for example, -2 is larger than 1 in terms of the amplitude of the U2, okay? So, and what is this term? This exponential term. This exponential term in the, it always have amplitude 1, right? So if you look at it, it's actually a sphere. Right, it's actually a sphere. So, right, e to the ix, right? No matter what your x is, the amplitude is always 1. The x only change where it's pointing, okay, where it's pointing on the polar system, on the polar coordinate, right? So now you want this exponential term at -1, you want it to be maximize the amplitude. And if you learn, well, if you're familiar with vector, then you know that when you add two vectors together and you try to maximize the length of that vector, the best way to do it is when those two vectors are pointing towards the same direction, right? Especially in this case, both vectors has a fixed amplitude. So the maximum, okay, this is -1. The maximum of this is that you have your exponential I 2k1 minus k2l, okay, equals -1, right? And then you add another -1 here, okay? And this is your maximum amplitude of this term, okay? And the minimum, of course, is very simple when you have this exponential term pointing to 1, and then you -1, then you get 0. Okay, so so what this means is that your E2, okay, has a maximum, and then the maximum is this term is 2, so you have 4 mu naught epsilon naught omega square pi 2. Okay. When this equals -1, so when, okay, 2k1 minus k2l equals equals 2n plus 1 pi, right? So pi n could equal to like -1, 0, 1, keep going, right? So when n equals 0, then this is pi, and then you plug in, okay, exponential minus I, well, exponential I pi equals -1, okay? So that tells you the maximum, well, that tells you the length that will optimize your output, okay? And that length is just the inverse of this. Okay. So this now is a very interesting observation, is that the maximum of your electric field of your harmonic light, okay, actually is decided by this term. Right? It's decided by the coefficient of your light, or coefficient of your nonlinear coefficient of your material, which makes sense. Okay, decided by the input strength of the input light. That's also makes sense, right? If you don't have input, then you shouldn't have any harmonic light. And also decided by the I'll call it, this is a phase mismatch, or you can call it wave vector mismatch between 2k1 and k2, right? And then one thing that you can see is that when this term is 0, right, if you can somehow match these two so that you can make this term 0, then E2 can really explode and can get very, very large, right? And when that happens, we call it phase matching. Later, I would explain a little bit more on this. Okay, so the takeaway here from this simple result is that longer nonlinear media doesn't necessarily give you stronger harmonic generation. And then second is that when you can match the wave vector, if you can match the wave vector, actually you can make the harmonic light very, very strong. Okay. Any questions so far? Okay. Now let's simplify a little bit of this expression because there's a lot of constant here, and then K1, K2, a lot of all this. Want to simplify this expression, and what we can do here is that we can plug in our definition of K, right? So in our definition, K, the wave vector equal to the refraction index omega divided by the speed of light, right? And then for the fundamental light, for the input pump, right, the omega frequency, so you will have K1 equal to N, you can call it N1 omega C. What N1 means is that the refraction index of this media at frequency omega, And K2 is N2 times 2 omega divided by C. You can make this 2 in the front, 2 in the front, and then N2 equals the refraction index at frequency 2 omega, And and for most materials, N1 doesn't equal to N2, right? There's whenever you have a media, and then the light will actually interact with your material, and that interaction, as we see previously in the linear model, that the refraction index is a function of your wavelength or a function of your frequency of the light, and this is called dispersion. So now what we can do is that we can simplify this. Oh yeah, one thing I forgot to mention. The physics meaning of y K1 equal to 2K1 equals K2, you will have the maximum amount of E2. The physics meaning of this is that this condition equivalent to momentum conservation. The momentum conservation of photon. I don't know if you guys have learned this before, but for photon, its energy is h bar omega, right? It's its energy. Its momentum is h bar k. K is the wave vector. This is the amount of momentum that each photon carries, right? And at first it might be hard to imagine why photon has momentum, but the fact is that if you shine a light, for example, on a piece of paper, the light actually carries a momentum, it has speed, and then it will actually it will create a little bit of pressure on this piece of paper. And then if you make the light strong enough, and then if you make the receiver of your photon very small, very thin, and very light, you can actually see this effect that the light is actually pushing, the light is actually pushing, in this case, the piece of paper, a little bit. And this effect is pretty serious, and then people have used it to, people actually have seen it in the LIGO, right, the light gravitational wave detector. The laser there is very powerful, and then people see that, the mirror can move a little bit because of this power. So this is momentum, And when you have 2k1 minus k2, what that means is 2. Let's multiply h bar on this side. 2k1 equals h bar k2. What it means is 2 times the momentum of the input light equal to the momentum of the harmonic photon. Okay, so what it really says, okay, is that this, if you look at the physics process of this, okay, what it really says is that those two photons that created the harmonic generation, okay, this phase matching condition, what it really says is that the momentum of these two photons, okay, is equal to the momentum of this harmonic generated photon, right? So this process means you have momentum conservation whenever 2k1 minus equal to k2, okay? And when a process satisfies momentum conservation and naturally satisfy energy conservation, that you have this process at its maximum efficiency. And that just makes perfect sense in a physics standpoint, okay? Okay, now, now if we plug in the k1 and k2, okay, their expression back in here in this equation, and then we can use a few, let's see. We can also, try to replace these two coefficients here, mu naught, epsilon naught. I think it's equal to 1 over c squared. Okay, you guys can check the Maxwell equation and then the wave equation we get in the first week. And if you do that, you plug in all this, you will have E2. Let's say max, okay, equal to 4 mu naught, epsilon naught now is 4 times 1 over c squared, okay, and then this is omega squared, okay, and then chi2 E1 squared divided by k2. K2 is 2 n2 omega, so 2 n2 omega divided by c. Okay, 2k1 minus k2, they have a common factor omega divided by c, so omega divided by c, and then you have 2 n1 minus n2, right? So you can see now here is that omega c can be cancelled with omega squared over c squared, and then 2 cancel with this, so eventually you will get 2 chi2 E1 squared 0 n2 2 n1 minus n2. Okay, let me just check. Somehow I missed the factor of 2 compared with my note. I'm not sure what happened. Let's see here. Oh, okay, there's a 2 here. Okay. 2 and 1, K2 is 2 and 2. Okay, so there's a 2 here. Okay, so when you have that, you have 4 up here, 2, 2. So eventually this expression is very simple. Okay, chi2 E1 squared n2 n1 minus n2. Okay, so very, very simple expression. Any questions so far? And of course, this is the expression at L equal to 2m plus 1 pi, okay, 2k1 minus k2. Okay. Okay. So now if you look at this equation, okay, whenever we get an equation, we try to make a connection, okay, with the experiment. That's a way that you can, that's actually the only way that you can verify whether your equation is correct or not. Okay, when you look at this equation, you see, okay, chi2 is just a material coefficient. There's a way to measure that, and people measure that all the time. And then N2, N1, N2, these are just refraction index. Of course, you can also measure them. And the only thing that's really a little bit weird is the electrical field, right? Usually when you have light propagating, and then when you get a piece of light, right, like from a laser, you don't measure the electric field because there's no easy way to directly measure that. Instead, what you measure, for example, is the power of that laser light. That's something very easy. You put, for example, you can, a very simple way is that you shine it on a piece of semiconductor, and then the photon, okay, the energy, the power, the photon, one photon can be converted to one electron, and then you count the number of electrons, and you know the number of photon, then you know the number of photon per second, okay, times the energy of the photon, h bar omega, will give you the power of the light. Also, another more simpler way is that you put a black box, okay, that absorbs the light, and then you measure the temperature change, right? That's the black box absorbs all the energy from the light and then converted it into a temperature change. Okay? So there are many, many ways that to measure the power of the light. So, so if we just stop here, right? If we just stop here, then there's no easy way for us to compare this with an actual experiment. So what we are going to do is to convert this equation into from electrical field into power, okay, optical power. And the equation we rely on is the same as before, right? We say this, the power of the light equal to N refraction index epsilon C A, okay, and then E squared. And A is the effective area, okay, of your light beam, right, of your beam. Okay, so this calculation is a little bit tedious, and then you can follow the notes on page 11 and page 12. But something that you can kind of anticipate, anticipate is that if you write this backwards, right, E2, okay, P divided by N epsilon C A, right? If you write it backwards, then you will see that for the same amount of power, okay, what you will get, same amount of power if you reduce the area of your beam, okay, then you will actually get a higher electrical field, right, higher electrical field. And later you can kind of anticipate, okay, that should play an effect because higher electrical field means higher effect, higher second order nonlinear effect. So later when you calculate this, the A should somehow appear also down here, okay? So now if we plug in this for E1 and E2, and then be a little bit careful about N, the coefficient N here, use N1, N2, then you will get P2, okay, the power of the harmonic generation, equal to 2 see, 2 chi2 squared, okay, P1 squared, N2 N1 squared delta N squared epsilon C and A. Okay, so this is an expression of harmonic generation in terms of the input power and output power at the maximum, at the optimized length, right? And this equation is something that you can measure. You can compare to the measurement in experiment. So a few observations here. One is that, okay, when we are trying to get harmonic generation, of course, we try to maximize the output light, right? Maximize the P2, right? So what you can see here is that while something very trivial or intuitive is that you want material of larger chi2, right? So stronger the chi2 effect, the more light you get. That's very trivial. The other thing is that's a little bit interesting is that the power dependent, right? So P2 actually depends on power P1 squared, and this very straightforward here. E2 depends on E1 squared, right? So when you get E2 squared to get the power, E1 would be to the fourth, and then give you P1 squared. So what it means is that if you want higher P2, you probably want a larger P1, right? If your P1 increased by 10, your P2 will increase by 100. Okay, so this effect is very, very, so higher power, okay, is very important in harmonic generation. And this is just the second harmonic. If you go to fourth harmonic, then this will be P1 to the fourth, and then eighth harmonic, right, P1 to the 16th. So large power is very important, and that's also the reason why, okay, the second harmonic generation was not observed, or was not discovered until the invention of laser. Okay, part of the reason is this P1 squared. Part of the reason is the phase, okay, phase stabilization of the laser. Laser is very stable, so that's how you can get the how in this calculation this term is. Think about it. That might not be correct. Okay, so the point here is that if you want second harmonic generation to be strong, you want a very strong P1 input. Okay, and then the second thing, well, the third thing after these two is the coefficient A, right? A is the area of the beam, and you might think, okay, this is just something, trivial, and then, but the fact is A can actually vary at a very large range. Okay, I'll give you an example here. So, for example, in free space, often if you try to focus a light and then make it parallel, okay, propagate parallel, and then usually A is on the order of millimeter square, right? That's the area, and that's 10 to the minus 6 meter square. Okay, that's in free space usually. You might wonder, okay, this is different from what you heard, right? What you heard is that in free space, when you focus a light, the minimum spot is determined by the diffraction limit, and then it's on the wavelength scale. That is true, but then when you focus light that tiny spot, what the light tend to do after focusing is that it will diverge very quickly, right? So it really doesn't. So it will diverge very quickly. So it doesn't really. It's no longer like a beam, okay, propagate from left to right. Instead, it's spread out everywhere, right? So if you want the beam to propagate steadily, usually, okay, the beam is like at the millimeter scale, okay. And the second is, okay, what about fiber, right? What is the effective mode area in a fiber? Fiber is something that people use all the time, okay. And in fiber, usually what it is in fiber, Okay, the center of the fiber, the core of the fiber, the diameter is around 10 micrometer. Okay, so if you square that you get your area, and that would be 10 to the minus 10 meters squared. Okay, fiber. So you can see that you can actually get a factor of 10,000 by simply moving from free space to fiber. Okay, moving from free space to fiber. And what can be more exciting is that fiber is probably not the best. Well, in terms of confining light in small space, fiber is not the best. Nowadays, a lot of people are working on, for example, waveguide, like silicon nitride waveguide, silicon waveguide, and all those waveguide. The cross section of those waveguide is around 1 micron. It's at the size of the wavelength of the light, right? So this gives you another factor of 2, another factor of 100. Okay, this is waveguide. So now, as you can see now, okay, moving from free space all the way down to the waveguide, what you will have is you will have a factor of 1,000,000, okay, in your effective area, right? So this is a huge gain that if you want to, let me put it this way, right? If you want to find a different material that can create the same effect, that material has to have 1,000 times larger chi2 compared to whatever material you're using right now. And that's typically very challenging for material science. Usually improve, within an order or within a little bit above an order of magnitude, that's fine, but have an increase of 10,000 is almost impossible, right? And also what this means is that coming from free space to waveguide, okay, because there's a factor of 1,000,000, then if you want to get the same, nonlinear, if you want to get the same harmonic generation, okay, same power, then your input power can be reduced by 1,000 times, right? P1 squared, 1,000 times, and that's a huge amount of improvement, right? If you're 1 milliwatt, which is, can be very damaging. If you start with 1 watt in free space, which is very, which can easily damage human eye and cause many injuries, and in waveguide you only need to use 1 milliwatt, right? 1,000 times smaller, and that's actually less power than your laser pointer, and then you can start to see this effect. Okay, so this area thing is actually the reason why people are now moving towards something called integrated photonics, using very small structures, and can observe effect at much lower power. And then this actually is a driven force for many information technology nowadays. Okay. Any questions here? Okay. If no, then we'll talk about the something that's very interesting in nonlinear optics is the phase matching delta n, right? You see here there's something that can really make this equation explode. Okay, the only thing that probably can make this equation explode is delta n, the refraction index between n2 and n1, right? If this goes to 0, right, then your P2, your power in your harmonic can also go, can go to infinite. And of course, that that's not physical, because when we do this calculation, we already assume that this is non-depletion regime. P2 has to be much smaller than P1. Okay, so that's this one really going to infinity. It's not physical. But something that you can easily see is that if you match this delta n, okay, if you decrease this, make it very small, then you typically get a free lunch, right? You don't have to change your material, you don't have to shrink your area, you don't need to increase your power, but you get a much better, much higher harmonic generation power, okay? So now let's talk about let's talk about how to make this N2 to 0. And this is called phase matching. The reason it's called phase matching is because if you look at it, this is in the phase term. 2k1 minus k2 is up here in the phase. And then when this term, delta n go to 0, 2k1 minus k2 goes to 0. So it's like their phase is always synchronized, right? So when you do this integration, E1 square always add up with another E1 square. There's no phase walk, here. So that's why it's called phase matching. And phase matching, the reason that we need phase matching, or the reason that phase matching does not automatically satisfy, is because we have dispersion. Right? If you plot in refraction index over, here I plot it over wavelength, you can convert that into frequency. For most materials, it will actually look like this. The longer the wavelength you go, the smaller the refraction index it has. And this actually makes a lot of sense, is because if you think about it, the longer the wavelength, if you use the wavelength as a scale for optics, then the longer the wavelength and the longer the wavelength, if you have this crystal structure here, right? This is a material crystal structure inside material. If your wavelength is very short, then for you, it's very easy to see these individual atoms, individual crystal atoms here, and you can interact with it very, very strongly. If you have very long wavelengths, now all of them are seen as continuous to you, and then your interaction with them are very, very weak. Very, very weak. So this is, and the stronger interaction of light between light and matter will typically give you a larger refraction index, and then slow the speed of light. Right? Just imagine like if there's no interaction at all, then the light just propagates as it is in the free space. As in the vacuum, right? And then you get the refraction index of 1, right? So, so typically, shorter wavelengths interact more strongly with the material, and you have larger refraction index. Now, for the harmonic generation, N1 is at omega, right? It's a longer frequency, because omega equals to lambda, equal to c times t equal to c 1 over f equals to c f is omega divided by 2 pi, so 2 pi, So lambda is 2 pi c divided by omega. So because lambda is this, and then you can see, this is lambda 1. And then when you have harmonic generation, then your lambda should be half of your lambda 1, lambda 2. Right, so you double your frequency, and then that means it's your wavelength reduced to the half. And if you look at this now, you will easily see that this graph, you can easily see that the refraction index for most materials, they should not match. They should not match at all. And for most material, this mismatch is actually very large. It can be on the order, usually on the order of 0.1. And if you know the refraction index is typically between 1 to 4, right? So 0.1 is almost like a few percent of change, right? So this is very serious. Now, so what technique? So people actually, found out this a long time ago. Now, what are the techniques that people discover, okay, to match this, to solve this phase matching problem? So one of the technique is called, is use is use birefringent crystal. Okay, birefringent crystal. What it is that you guys can actually go to the YouTube playlist, and then there's a video I put in there. There's a professor there demonstrating the effect of birefringent crystal. What it is that if you think about it, it actually makes a lot of sense. Is that suppose now you have a crystal that's not, let's say that's not a trivial one, for example, the x direction, and this is the y direction. So at the x direction, the crystal are much closer. Well, the atoms are much closer, and the y direction, the atoms are much less dense. Right, the spacing is much further, is larger than the spacing in x. Right. So now, if you think about it, if there's a light, its electrical field is at x direction, right? Then its interaction with the atoms should be much stronger than if the electrical field is pointing towards y direction, right? Because that y direction is much harder to it's much harder to meet the next atom, right? So for in crystal structure, it's very, very common that you have more than one. You don't just have one refraction index. Okay, your refraction index actually depend on the the direction of your light going into that crystal, and then the polarization of your light. Okay, where at what direction your electrical field is pointing towards, and this will give you a different refraction index. Okay, when your wave have different. When your electrical field is pointing towards different direction, okay, and a very basic picture that you can use to kind of help us to calculate this, okay, also to understand this, is that suppose this is a crystal, and then you have light coming in from the left, okay, and then going out from the right, of course. And we define something called, and because of this, right, we can define, let's point one more thing is that there's something called optical axis of this crystal. Later I will explain what the optical axis is, okay. And, and so now because the light, let's assume that it's transverse a light, right, so the electrical field is always perpendicular to the propagation direction of the light, right? So you can kind of define two types of wave. One is called ordinary wave. Ordinary wave. What it is that ordinary wave is that its electrical field is going in and out of this whiteboard. Okay, so it's perpendicular to the propagation direction of your light. And it's also perpendicular to the plane, okay, it's perpendicular to the plane formed by the crystal optical axis, and then your propagation direction, right? So this one is always perpendicular to both your optical crystal axis, and then also your propagation direction of the light. Okay, so that's we call ordinary wave. Later I will explain why it's ordinary. And the other direction we call it extraordinary. Right? One is ordinary, the other of course is extraordinary. That it's in the plane, okay, with your optical axis, and then your in the plane formed by your optical axis, and then your propagation direction of the light. Okay. Now, what is the optical axis. The optical axis is something you can imagine is that it's something, it's the symmetric axis of a crystal. What it means is that, okay, if from an experimental point of view, is that if you have a light propagating along the direction of the optical axis, then there will be no optical birefringing effect. There's no two refraction index. There's only one refraction index if your light propagates along this optical axis direction. Okay, this is how experimentally you can define, you can find the optical axis. And then the other way that you can kind of define it is that the optical property about this crystal is symmetric along this crystal line, around this axis. That's why, okay, when the light propagates along this direction, no matter what its polarization is, it always just have one refraction index. Okay, so that's from the symmetry argument. Okay, now, and then the angle between your optical axis and then the propagation direction of the wave of the light can be defined as theta. And now, something that we know, people actually know for a long time, is the for a long time is that the extraordinary wave and ordinary wave, they will have the extraordinary wave and ordinary wave, you can define, you can actually measure two different refraction index. Okay, one is, let's put it this way, one is ordinary, as here. The other is extraordinary, which is here. Extraordinary. And the extraordinary and the extraordinary NE, okay, how we define this is that when you have light, okay, propagate in this direction, this is ordinary, this is extraordinary, okay. The extraordinary refraction index, okay, of this light going up and down, and then with your optical axis offset a little bit with your having an angle with your wave propagation distance direction, is sine square theta NE square plus cosine square theta N naught square. Okay, so now you can see what this NE really mean here now. NE theta. Okay, so N naught ordinary wave is very simple. Is when theta is 0, right? Then cosine theta is 1, sine theta is 0. Then NE equals NO, right? So that's what we say when you have a light. When theta is 0, C, okay, is the same as K. So that's what we say, that when your light is propagating along the optical axis, then your refraction index is the same for both extraordinary and ordinary. There's no birefringing effect. Okay. Now, when you're not at the same direction, when you have an angle, then your extraordinary light, okay, this polarization, its refraction index, can be expressed in this equation. And then there's a special case when theta equals to 90 degrees, right? When theta equals 90 degrees, then your wave direction, propagation direction, is perpendicular to your optical axis, but your extraordinary wave, its polarization align with your optical axis. Okay, in that case, you will have NE 90 degree equals to NE. Okay, so this is the NE that we plot here. Is when the light is perpendicular to your optical axis propagation, and then your extraordinary electrical field, okay, is the same direction as your optical axis, okay, then your refraction index is the NE, okay, it's the NE. And usually these two are quite different depending on different crystals, but usually they're very different. And then something that you can do here, let's make it a little bit more dramatic. Okay. Usually they're very different, and then they don't naturally match for your harmonic generation, right? They don't naturally match. But you can see that the NE, the extraordinary wave, its refraction index, okay, its refraction index is in between an ordinary wave refraction index and then completely extraordinary wave refraction index, right? So what you can do now is that you can tune the angle theta, okay, tune your crystal, and then you can change the theta so that you can make NE theta, okay, equal to N naught, okay, equal to ordinary wave. So that what you will have is that you will have your light, input light, as an ordinary wave, and then your output light, harmonic generation, as an extraordinary wave. Okay, and then you tune the angle so that you can do this phase matching, and then this delta n can actually approach 0. Okay. And this is a method called angle matching, angle phase matching. And in the note, actually, I explained a little bit that the angle phase matching is not perfect, because when you have this birefringent effect, and then when you have this extraordinary wave, you can go in there and then calculate the direction of energy propagation. It's not always along the k direction anymore. You can use the Poynting vector to calculate that. There's actually a walk-off, something called. So for angle phase matching method, usually, okay, the interaction length, the L, okay, has a maximum. So you cannot say, okay, this go to 0, L go to infinity, and then you always have a very large, you can have extremely large harmonic generation. That doesn't really happen. Okay, now let's move on, and then one more thing I want to comment is that in the experiment, people just not only tune the angle, right? Because in the experiment, once you find the angle, you kind of keep it there. What people do next usually is that they also tune the temperature of the crystal. Okay, what that would do is that it will shift the refraction index of ordinary wave and extraordinary wave, and then their change would be slightly different, and you can fine tune, okay, to make your delta n goes to 0. So that's also called temperature tuning of phase matching. Now, now I want to talk about a technique that people actually use a lot more in nowadays. It's actually proposed a long time ago, but then it's not really the mainstream until 1990s, and then the reason is limited by the fabrication technique. Okay, the method for phase matching, okay, another popular method nowadays is called quasi-phase matching. Oh, I shouldn't erase you. Okay, quasi-phase matching. Okay, what quasi-phase matching is when we look at this equation, again, it's the same equation we solve. Okay, we see that the oscillation or what's really, if this is not zero, right? If this is not zero, then if you plot, the integration of this, you will see that, okay, at first, let's say the vector is pointing this way, and then later goes this way, this way. This is real, imaginary, right? At first, it's purely imaginary, and then keep going, going, going. Right. The point is that it would start to do this circle, right? The phase is doing this rotation. Right, so that's the reason why you cannot continuously increase your harmonic generation. Is because of this rotation of the phase. Okay, and of course, in phase matching, what people do is try to make this K1, the phase mismatch, as small as possible, so that you always kind of stay in the same regime, and then the integration can add up together. And a very clever method that people actually came up with is that, okay, what if we look at the Z and E, right? In the phase well, if you do integration, right, and then write this down, you will see that the energy, okay, oscillate, as we say, along the distance of Z. What if, and the reason for this is that this part, the left part, and then the right part, okay, their phase is off by 180 degrees, right? So whatever you are doing here would eventually be canceled out by this part, and then you go back to zero. Okay, so the quasi-phase matching is actually the idea that, okay, what if in this region you have okay, you have this phase factor here, and then you integrate over here, and then you go from 0 to pi, right? But now here, what if I add a minus sign here? Right? I add a minus sign here. And by adding this minus sign, previously you should go from pi to 2 pi and then completely cancel out 0 to pi, right? But whenever you add a minus sign, okay, to your cosine or sine, what it does is that it no longer goes down. Okay, originally wants to go down, but now with the minus sign, it continues to go up. Right? It's like with this minus sign, you can change your phase. Okay, you can actually change your phase, offset your phase by 180 degrees. Okay, and then let it continue to go up. Yeah, one thing, by the way, is that if you guys want, really a good quality of teaching, like online teaching, one way is actually you actually need to show up in the in the Zoom call, because right now, if I just talk to the camera nonstop for 1 hour, the energy level really drop down, and then you will not see the same lecture level or lecture quality as I'm talking to directly to students. Okay, so if you somehow find that sometimes I, stop and then lose focus, just try to understand. Okay, and yeah, I'm just right now at this point. So okay, yeah. So how can we do this? How can we do this? And then people actually find out a method is that what you can do is that you have light input into a piece of crystal, and then in this crystal you have the first cell with its optical axis pointing upward, and then the next cell, okay, pointing reverse downward, and then you keep going upward, downward, upward, downward. Okay, what this would do, is that for the chi2 coefficient here, okay, in this cell, if it's, let's say if it's positive, then in this cell it will become negative. Okay, it will become negative. And the reason for this is that if you think about it, if the polarization is this direction, okay, if you think about it, is by looking at the very simple nonlinear polarization equation. Okay. Now, usually, okay, the direction you can define along with the optical axis. And now, if your optical axis is reversed, right? It's reversed, and let's say your coordinate follow the optical axis, then what you will have is that you will have your polarization, nonlinear polarization, go from P to minus P, right? Because if it's pointing upward, now your axis flip, right? Then your polarization will pointing upward will be minus now, okay? And the same apply to the electrical field, right? In the axis we're down, okay, when you reflect the coordinate, okay, your electrical field become minus, okay. Now you plug in all this into this equation, right? It's still the same crystal, so they should satisfy the same equation. Then what you will have is that you will have minus P, okay, equal to mu naught chi, and then you have 2e here, and then they flip sign. They all flip sign, so you flip sign twice, equal to not flipping sign. Okay, so the net result is this, minus. Okay, so because of this, the net effect, okay, when you have a crystal pointing upward, and then now the next crystal pointing downwards, the net effect is that it looks like, okay, your chi2 flip a sign. Okay, your chi2 flip a sign. Later, next class, when we talk about what we need for non-zero chi2, we'll actually go into symmetry argument a little bit more. Okay, but what this can do is every time, okay, when this cycle let's say first this is real, right? So when the cycle goes down to here, goes this way, and then you flip, and then if you don't have this minus sign, then you will try to complete this cycle, and then you end up the integration is 0. Okay, then what you're really doing is that, okay, then if you have a minus sign, then you flip this up to this side, and then you continue to add up all the terms here. Okay, you can do there's a simple calculation on the note at page 18, okay, and then show you that with quasi-phase matching, okay, your field can keep increasing, okay, like this. Okay, and that's all for today. Okay, thank you.